Hello and what's up to your grade 10 mindsetters. Welcome to it. It is a new term for your physical sciences. My name is Abram and I'm joined by Mr. TK to learn more and learn extra right here on your favorite learning show. Mr. TK, how are you?
I'm good. And you, Abram?
I'm doing well, so I can't complain. It's a new term, new beginnings. For some mindsetters, it was a holiday, but for others, it was work all the way.
Yes, especially if you are a physical sciences learner, there is no holiday really. Even when you are at home, you sit and you work, you do all these problems, you revise your work, just to make sure that you are on par with everything that you're supposed to do, and you are on your toes really throughout the year.
All right,
That's the life of a science learner.
Well, clearly that means you also didn't have a holiday.
No, not really. You can't have a holiday. As a teacher, I
Not
had to
really.
be weak. No. It's just a holiday because you are not in the classroom, you are at home, but you have to find a space for yourself to study and do something about that time. It's so important.
All right, I like that. My sisters, do share with me. If you were on holiday, let me know what were you doing. Were you studying or not? If you're just chilling at home, resting, watching TV, and eating every day, still share with me on Facebook. But what are we doing today?
Well, today we're doing longitudinal waves, and we'll bring sound into it because when we talk longitudinal waves, we're talking more about sound. I mean, sound is one example of longitudinal waves. So that's what we'll be talking about for grade 10s. And I think I'm taking grade 10s for the first time in 2014. Yes.
Wow, well done. I hope you're going to enjoy it as much as the mindsetters are.
Definitely, I am going to enjoy it, and I hope you're going to learn more out there.
Awesome. Well, mindsetters, to take part on this show, make sure that you log on to your Facebook account on facebook.com/learnextra. Like the page if you've already liked the page. Share the page with your friends, your classmates, even your teachers or your group mates. Make sure that everybody is on the same page as us. It is Learn Extra on Facebook. Otherwise, you can also download your notes on learn.mindset.co.za. But to help you this new term, we're beginning with new innovations, Mr. TK. You know that in the last term, mindsetters will just download the notes. We'll give them a link to download the notes. But now we've made things more simple for everybody, whether using a smartphone or not a smartphone. As long as you can go through the internet, you can view the notes or download the notes. So those are the two innovations, options that you have, mindsetters. A direct link of viewing the notes. As Mr. K is going through the notes, you can view them. And the second option is to download the notes. But otherwise, follow me on Twitter at LearnExtra. That's where we're going to be taking each other on a journey of tweeting, and I'll read some of your tweets later on. If you have some questions, feel free to throw them at me because I'll be taking them through to Mr. TK. But for now, let the learning begin.
Thank you so much, Abram. And let's just start. Like I said, we're talking longitudinal waves today. And in this lesson, we're going to be talking about those longitudinal pulses. Don't worry about what pulses are, and because we're going to explain that. So pulses and waves, that's the main issue here, the main theme of the lesson today. We're also going to revise properties of sound. Okay, so I'm going to give you a brief description of or revision of what sound is so that you can understand what is the link between wave and sound and all those things. We're also going to look at solving some of the problems that are related to sound waves. Okay, so that is what this lesson is about today. Now, remember, we always have the challenge question for you. Now, the challenge question for today, which you need to start working on because we're going to come back to it right at the end of the lesson, it's as follows. It says calculate the speed of sound in air, all right? If it takes 2.8 seconds from the time you produce a sound till the time you hear the echo of that sound. So you need to know what an echo is. Till you hear the echo of that sound, the distance from you to the reflecting surface where this sound is reflected from to come back to you as an echo, it's 475 meters. So that's all I could give you. That's all the clues I could give you for this question here. Just go sit down, work on it, and towards the end, we'll come back to it. Now, let's get to the lesson for today, going through some notes, going through some pointers and critical points within this theory of waves and sound. Look, here we are told that we're talking transverse pulses. What is a transverse pulse? We're going to look at it now. But firstly, when we talk of waves, waves move in medium. And a medium in which a wave is moving, it's actually, or we can define it as a substance or material through which a pulse or a wave moves. So that is a medium. So when you hear sound, it doesn't just come to you. Some medium allows it to travel from the source of sound to where you are. So that's what we mean by the medium. A pulse, on the other hand, is defined as a single disturbance which moves through a medium. So if I've got some medium, say this one here, I've brought some slinky for you to see here, to see how waves can be propagated. This is my medium. If I disturb it by doing that, I have caused a disturbance, I have caused a pulse. So a pulse is a single disturbance which moves through a medium. Now, if this, say my left hand is a fixed position and I disturb it this side, you can see that there's something moving from this point to where the fixed point is. And from the fixed point, it is actually coming back as well. So you can actually see the wave repropagating itself. So when I go like that, it comes back. So that's what we mean. I disturb it and on one point and it moves through the medium, which in this case is my slinky here. So that's how you define it, a pulse, a disturbance which moves through a medium. Okay, now, when we're talking about a transverse pulse, which will of course lead to a transverse wave, a transverse pulse is formed in a medium when all the particles disturbed by the pulse move perpendicular, or what we call at right angle to the direction in which the pulse is moving. Now, how can we demonstrate that? Again, let's go back to what I had before. Here is my slinky. My fixed position is my left hand, so I disturb it this side. Okay? When I disturb it this side, the pulse is moving in that direction. But where is the disturbance? The disturbance is upwards. So the direction of movement of the pulse is this way, but the disturbance is that way. So there's a 90-degree angle between the disturbance, which is the pulse, and the direction of motion of the pulse. Okay, and when you have that, we have what we call transverse pulse. And because that pulse now you propagate one, or you have one disturbance, but you have got series of them moving there, you end up having what we call a transverse wave. A transverse wave is one where the direction of motion of the wave is at an angle to the direction of, or to the disturbance, or what we call the pulse. All right. On the other hand, we do have what we call longitudinal pulse. A longitudinal pulse is formed in a medium when all the particles disturbed by the pulse move parallel to the direction in which the pulse is moving. Okay, so what would be this kind of a wave? If I have my slinky at its resting position like that, and I decide to disturb it like that, I've got a pulse on this medium now, but the pulse, as it moves in the medium, you will see that the pulse is moving in that direction, and the disturbance is actually in that direction, and the disturbance is in that direction, and the movement of the pulse is also in that direction. And when it goes up, you can see it goes up and backwards. So you can see the direction is up there and coming backwards. But the fact remains that the direction of disturbance and the direction of motion of the pulse are actually parallel to each other. That's when we have longitudinal pulses. And that would lead us to having what we call longitudinal waves, of course. All right? So that's how it forms. So the direction of motion of the pulse is parallel to the direction in which the pulse is moving. So the direction of disturbance is the same, is actually parallel to the direction of the pulse. Okay, so that's what it means there. Next, we also need to talk about something called the amplitude. The amplitude of a pulse is a measurement of how far the medium is displaced, momentarily, of course, from its rest position. Okay, so if I have that, okay, let me make one big pulse like that. This distance from the rest position to the top, from here to the top there, becomes what we call the amplitude. That is how far the medium has been displaced from its rest position. When we're talking longitudinal waves, we will be talking about things called compressions and rarefactions. What are compressions? A compression is a region in a longitudinal wave where the particles are closest to each other. Okay? Now, look at it. Okay? As that happens, there are times when these particles are far apart from each other, and there are times when these particles are closest to each other. And when they are far apart from each other, that point where they are furthest apart from each other, we call that a rarefaction. Okay? But when they are closest to each other, like at that position, say it comes to that position, at that position we would have what we call a compression. Okay? So that is how you define these terms when you are asked to do so in an exam or in your exercises. All right. Now, quickly, let's just have a look at some of this, at this diagram here, which talks to compressions and rarefactions. Okay, so look at that. That's when these particles are far apart from each other. So you have a rarefaction. And here, obviously, close to each other. In fact, I should have stopped there. That's when you're having a compression. Okay, so as shown in your diagram there. Okay, the wavelength in a longitudinal wave is the distance between two consecutive points that are in phase. That is, between two consecutive compressions or two consecutive rarefactions. Okay, so where would I have a wavelength here? You would see that from this point to that point, because those 2 points are from, okay, these two, from this point to that point, okay, consecutive rarefactions, you would have a wavelength, and in that order you have what we call a wavelength. You can actually work it out or show it out in diagrams. And quickly, we have something called interference. In interference, we can have constructive interference or destructive interference. When pulses move towards each other and they are in phase, like this two here, they may end up reinforcing each other and coming up with a bigger amplitude like that at the end. And we call this constructive interference. If this was 2 centimeters and that was 2 centimeters, now we are having 4 centimeters there if they actually meet together. That's interference. Now, we can also have pulses that are out of phase like this two here and moving in opposite directions to each other. And you would see that when they come together, they give you a destructive interference. In other words, there is no more that pulse or that pulse. It is leveling up there. This is no more there, and that is no more there. Hence, we call it destructive interference. They have destroyed each other. Okay, so that's very critical for you to note as well. Now, quickly, when a source of sound Okay, now we're linking sound to waves. When a source of the sound vibrates, it creates regions of high pressure and regions of low pressure. Okay, so that happens, the rarefunctions and compressions. Speed of sound waves depend on the medium. So how fast a sound wave is going to move will depend on in which type of a medium is it moving. Is it moving in solids, in air, in liquids, things like that. Okay. Let's look at this. If you have got solids, the particles are very close together, okay? And for that reason, the sound waves are going to move very faster in solids because the particles are together. They actually vibrate and connect with each other quite quickly. So the sound will move faster there. When we look at what happens in terms of temperature, if you have higher temperature, it means that your particles, be it gas molecules, they are moving faster. And if they move faster because of a higher kinetic energy level, the sound waves in hot air will move very fast. Okay. When we talk of air pressures, for example, higher air pressure, remember, if you have got higher air pressure, it means you have compressed the gas. The molecules of the gas are closer to each other, just like in solids. And therefore, we expect the speed of sound in high pressures to be faster. Okay, so in higher pressures, it will be faster. And this is found normally at sea level, where air is denser. Okay, now quickly, the pitch of sound. Pitch of sound relates to the frequency, okay? This, for example, if you've got a middle C note at the frequency of 256 hertz, okay? If that frequency would refer to the pitch, that is the only thing that refers to the pitch of the sound. Now, the higher the pitch, the higher the frequency. If you look at this part here, we've got a higher frequency in this wave here, sound A, because we've got more like 2 complete waves in the same set of time. But here we only have 1 complete wave in 1 set of time. And therefore, here we've got lower frequency and higher frequency here. So you can say lower pitch here and a higher pitch this side. Okay? If you like, because frequency is related to pitch. Now, the human ear can detect frequencies from 20 to 20,000 hertz. Those are audible to the human ear. If it's anything less than that, okay, less than 20 hertz, we will not be able to hear that. And that type of sound is said to be infrasound. Okay, infrasound, we can't hear that. If it is greater than the 2,000 hertz, we call this ultrasound. Much higher than the frequency that a human ear can detect. Okay, so it's ultrasound. So that's what we have in our theory here. I hope you have done or you have learned quite a lot from here, and you have seen the link between the theory on waves and sound waves in particular, because that is where we're getting to. Application of our knowledge of waves into sound.
Thank you so much, sir. Well, on Facebook, there are so many mindsetters chatting with me, such as Ishmael Paling saying, I'm just going to enjoy my birthday evening watching my favorite show with the mindsetters enjoying the lesson with Abraham and our new teacher. Welcome, new teacher. And happy birthday to you, Ishmael. You're sharing your birthday with me. I hope you're enjoying your evening as much as I am enjoying mine. Otherwise, mindsetters, we'll see you after this break. Welcome back, awesome mindsetters. Now we have a Facebook app that is currently working as our help desk. I'd urge all of you mindsetters to go visit it. Click on the link that is provided on your Facebook page, which is facebook.com/learnextra. Check out the help desk, because it also it also has some FAQs, so you can check them out or send us your own questions. But for this show, if you're struggling anyway, we're here to help you with Mr. TK. Send through your questions and we'll take them later on.
Definitely. Let's
But
just...
but also importantly, the
Yeah.
challenge question is posted on Facebook, so
Yes.
give it a try and we'll do the solution later on.
Yeah, we'll have that done towards the end of the lesson. And here now I've got a set of questions that we're going to go through, and we're going to practice through them together with me. So make sure you sit, you have your book, you have your pen, you have your calculator, you're a science learner, and therefore there's no way that you're going to have that Oscilloscope calculator with you. You have got a beautiful scientific calculator with you that you are using.
I feel like I should jump in.
Really?
I feel like I should jump in and tell the mindsetters that if you're using that Oscilloscope calculator,
Yeah.
worry not, because next week we're having a competition that is kickstarting from Monday. It is proudly sponsored by Casio. So we'll be giving away calculators.
Beautiful, beautiful. So stay tuned, stay tuned. Be part of these lessons all the time. Now let's come to our question here. The first question under improve your skills. So we'll be learning on how to work out solutions to problems based on sound questions or wave questions. Let's have a look at this one here. Question number 1. A guitar string produces a musical note, and the E, this is an E note, all right? And thus travels through air at a speed of 330 meters per second. The frequency of the note is 329.6 hertz. Calculate the period of the note. Now, look, you are to calculate for the period of the note. By the way, what is the symbol for, the scientific symbol for period when we're talking waves? It is capital letter T. So you write your capital letter T and you say it is equal to. And what is that equation or that formula that gives us the period of the wave? When we have, look what you are given here. You are given your frequency, you are given the speed of the waves, of the sound wave in air, all right? Now, period, you must know, it is always given by 1 over F, okay? 1 over frequency, all right? So what is 1 over frequency here? Our frequency is 329.6 hertz, or per second, if you like, all right? Because a hertz is an equivalent unit for per second, all right? So then that works out to, no, you don't have to crack your skull about this. You bring your calculator on and just say, okay, I've got 1 divided by 329, 329.6. And what is my answer? And you find that to be 0.003, all right? So that is 0.003, 0.003. 3 what? Remember, you are dividing by per second. So this is second. Period is measured, it's time. It is measured in seconds. So this is 0.03 seconds, okay? Just putting it in full so that you don't mistake my S there for 5. It's 0.003 seconds. All right, that's your period. Don't forget this formula here. It's critical when we're talking waves. Right now, the next question is find the wavelength of the note. Now, the wavelength is lambda, that symbol there. And because we are given the speed in which the sound wave is moving in air, and we are given the frequency, we can actually go straight to the wave equation. And what is that wave equation? You must remember it. The wave equation is V equals F times lambda. This is your wave equation, all right? And we are given the V is given to us as 330 meters per second. And the lambda is, the frequency is 329.6. So all we need to do is to substitute into this. So 330 meters per second equals to 329.6 times lambda. Therefore, we can find what lambda is. Lambda will be 330 divided by 329.6. All right? And what will that be? Again, you bring your calculator. All right? We've got 330 divided by 329.6. And what's the answer? We find lambda, which is the wavelength, to be 1.0 meters. Okay, remember that wavelength lambda is measured in meters because it's a distance between two consecutive points that are in phase in a wave. Okay, good. Now, moving on. A different string on the guitar also produces a note. So I'll put that here. Also produces a note with a frequency of 82.41 hertz. And this note is also an E note. Can I have an E note with different frequencies? Yes, because I can have different pitches from different strings of a guitar. Okay, so the pitch of one string may not necessarily be the same as the pitch of the other string, but they may be working on the same note. For example, your thicker strings on the guitar versus the lighter ones, thin ones, they won't produce the same pitch for the same type of notes. All right, so that is where it comes from. Then the question here is, you have got 82.41 hertz for your the second string there on your guitar. All right? What can you deduce about these two notes or these two strings? Okay? These two strings, sorry about that, which produces the same note. Okay. So what is happening here is that you have got the first one that we spoke about. The first string produces a higher pitch. Why? It is producing a higher pitch because it has a higher frequency. Okay? If you remember well, the frequency that it has is the 329.6 hertz. Now, this is much higher than the second one. Okay? So this is what we are deducing from this. So I can also say that for the second one, the second string produces a lower pitch. Okay? Why? It has a lower frequency. Okay? So lower frequency, lower pitch. Higher frequency, higher pitch. And you can see that the frequency that we are given here for the second string is 82.41 hertz. Now, far, far lower compared to the 329.6 hertz, which was the first string that we looked at. Okay, so this is very important. The main idea here is to link frequency to the pitch of sound. Now, there's also this one that I need to quickly talk to you about before we move on. Whilst you link frequency to the pitch, the loudness of sound is linked to the amplitude of that sound wave. Okay, so with a 2 centimeter amplitude of a wave would not be so loud compared to one that is 5 centimeters. Okay, so the 5 centimeter one will be much louder. The amplitude, remember the amplitude? That's what the loudness of the sound is related to. Right. Moving on to question number 2. A teacher uses a signal generator to produce sound waves which have a frequency of 10 hertz. So we've got 10 hertz frequency and a wavelength of 40 meters in air. The signal generator is attached to an oscilloscope. A wave pattern is displayed on the screen with an amplitude of 2 centimeters. Remember what I said about the amplitude? Relates to the loudness of the sound. The oscilloscope is adjusted to show 2.5 seconds. All right? Now, 2.5 seconds, draw a sketch graph showing what you would see on the screen. Now, if my frequency is 10 hertz, it means I've got 10 complete waves. I've got 10. Oh. I've got 10 complete waves passing a point in 1 second. Okay? So let's go back to this. 10 complete waves passing a point. In 1 second. So if I have a time interval that is given to me to be 2.5 seconds, how many complete waves am I going to have there? In 1 second I've got 10. It means in 0.1 second I would have 1 complete wave. Okay? 1 complete wave. So in my graph here, if I were to draw, so let's come to the question here. It says, draw a sketch graph showing what you would see, what you would notice on the screen. All right? In my graph here, the amplitude has to be 2 centimeters. So I would have 2 there, and then my minus 2 centimeters there. So that is my maximum point. Okay. So at 0.1, I would have a full wave. 0.2, 0.3. Oh, sorry. So I need to make this longer so that we can have a nice shape coming up here. Okay, so allow me to have my 0.1 there and my 0.2 here and my 0.3 there. Okay, so halfway in between will be my 0.25. In fact, okay, so in this 2.5 seconds should have been 0.25 seconds. Sorry about that. So let's put it like that so that we can have a shape, a nice shape of our graph here. Right, so drawing that graph, I have a complete wave here, all right? And I would have a complete wave there. And obviously when it's 0.25 and a half, I will have something like that, okay? Pardon my drawing there, but this is a neat wave. Look at it as a very, very neat wave as it is. Now, that's what I will see or perceive on the oscilloscope, on that screen. That's what will be happening. The next question here, which is question number B, says, on the same set of axes, draw a graph showing a wave that has double the amplitude and half the frequency. Double the amplitude and half the frequency. All right, now, if it has got double the amplitude, it means it will come to some point here where you have, say, it will be 4 centimeters. Okay, so this would be up there. And you will have a wave, it's double the amplitude and half the frequency. When you halve the frequency, you double the wavelength. So what it means is that I would have my wave this time going like that. I need to bring my, let me just do that. So I'll have my, what was a full wave is now half the wavelength. Okay? Half the wavelength, like that. And obviously, it would have gone much down this side as well. Look at it. Because it must go to 4, come back there, and then it goes up to 4 as well. But it can only go to that point there, which is the point of 0.25. So that's what I would have if we double the amplitude and half the frequency. This is the shape that we'll see or perceive on the oscilloscope. All right. All right, and the next one says, calculate the speed of the sound wave. Now, this is easier. You go back to the wave equation, as I've told you. Now, V will be equal to, remember we are given frequency. Frequency is 10, and the wavelength is 40. And therefore, the speed of the wave is 400 meters per second. That's what it is, okay? Quick and straightforward with that one. Don't forget, like I said, with the other equations, the period, don't forget your wave equation. It's very critical for you to know and use at this stage. Okay, now quickly, predict what will happen to the speed of sound when the sound moves from air into still bar. Look, with air, we have got particles that are far apart. With a still bar, we've got particles that are closer together because this is a solid. So what will happen to the speed? The speed of sound will increase. Okay? Moves faster in solid. Moves faster in solids. Okay, so don't forget that. What will happen if the sound wave moves from air that is moves from air, normal air in that speed to an air that is 5 degrees cooler. Now look, if it is cooler, you have got less kinetic energy, okay? Molecules move slower, so molecules move slower, all right? And when molecules move slower, that means the speed of sound decreases, okay? Now, this is the issue of temperature. The higher the temperature, the faster the sound in that medium. The lower the temperature, the slower the sound movement in that medium, right?
Thank you, Mr. TK.
Yeah, boy.
It's time for a break, sir. And mind tutors, you have so much to do during this break. There is a challenge question that is posted on facebook.com/learnextra. And also, if you're having some questions, feel free also to throw them in, and I'll take them, because after this, we're going to be answering your questions. See you after this break. Welcome back, Mindsetters. If you just joined us now, you're a bit late, but you can still catch up. Do the challenge question that is on facebook.com/learnextra, and also send us some tweets at learnextra. Follow us, and we can read some tweets, because already on Twitter, there's some people saying they're enjoying the show. Welcome to the new teacher. It's like they're singing for the first time, eh?
The great ones, yes.
But
They
I
don't
guess,
watch. It means they don't watch the other lessons. Grade 11 and 12, they don't watch
yeah,
it.
you know, great hands are like, Aish, it's 5 o'clock. Done.
Yes,
I'm not going
school
anywhere.
out.
But otherwise, if you still have some questions, send us through on facebook.com/learnextra. Back to you, sir.
Thank you, Abram. Abram, and we're moving on to this challenge question. Remember, you had a time to work on it, so during breaks, you had to be working on it. I believe you already have your answers to this problem now. So let's see how you were supposed to approach it, and let's see if you got it correct. If you haven't done it yet, do it with us as well now. All right. Okay. It says here, calculate the speed. So it's the speed that we're going to look at of sound in air. If it takes 2.8 seconds from the time you produce a sound till the time you hear the echo of that sound, the distance from you to the reflecting surface is 475. Okay? So let's see. You've got a distance from you to the reflecting surface. In other words, your sound goes as you produce it, it hits that surface, and it comes back, and you hear it as an echo. You're not saying it anymore, not shouting it out, but you hear it again as an echo. So it came back to you, it hit that surface and came back to you. All right, that distance is 475 meters. And it took 2.8 seconds to come back to you from the moment you produce the sound to the moment you hear it again as an echo. It took 2.8 seconds. Okay, so that is the time it took. Then the question is, find the speed of sound in air that day when you did that sound, speed of sound. Okay, how are you going to get it? One thing for sure, if the distance from where you produce the sound to where the reflecting surface is 475 meters, it would mean that the sound traveled from you 475 meters to the surface, the reflecting surface, and traveled another 475 meters back to where you are. So basically, the total distance moved by that sound is twice that distance. So you would therefore say that total distance is what? Is equal to, total distance is equal to 2 times 475. Okay? And that will be what? Okay, you can work it out from your calculator. 2 times 475. All right? As I know, I don't want to make any mistake here, so you do the same. So that is 950. Okay? So 950 equal to 950 meters. Right? So that's what you have. Now, from this information, you can then use the general, like I said, general speed formula. All right? And what does it say? Speed is equal to distance moved divided by time taken. All right? So this will be 950 divided by the 2.8 seconds. 950 meters divided by 2.8 seconds. What will that be? Go back to your calculator. 950 divided by 2,8, and you get 339,29. 339,29. All right. 339,29 what? Meters per second. Where does that meters per second come from? This is 950 meters. This is 2,8 seconds. So that meters per second comes from meters divided by second. Okay, and that is the unit of measurement for speed or velocity. Okay, so that was the challenge question, and I hope most of you must have gotten that right, unless you didn't see the fact that the distance had to be doubled because the sound went, got reflected, came back, and it took 2,8 seconds, and therefore it was double the distance. Do we have some questions?
Well done to all the mindsetters that took a chance and they got the right answer. And if you didn't get it the right answer, you probably see where you have made your mistake and you can still fix that.
Definitely, yes.
Right.
Yeah.
Here's a question, the first one from Hunadi. What is the tone
Hunadi.
of a sound?
The tone
Yes.
is all right. Good question anyway. Tone, scientifically, we don't talk about the tone of the sound. We talk about the pitch of the note. Okay, so turn this around and say note. All right, and say note. Okay, so we're talking about the note. And that note, it is that sound wave that we're talking about that would be having a frequency which is related to the pitch of the of that note, okay? And obviously, if there's got frequency, it's gonna have the wavelength. All right? It's gonna have the wavelength, lambda. This is frequency F. And from the two, it will have the speed. Okay? So we will be talking about a note, not the tone. Now, the tone of talking, and I don't like the tone at which you're speaking to me. Now, that's not what we basically talking about here, but we're talking about those sound waves. Of course, as you speak, you're creating sound waves. The tone, as you very harshly speak to somebody, you are actually working more on your loudness, okay, or the amplitude of your sound wave, not necessarily the pitch or the frequency. All right. Generally, each one would have the same frequency.
So true. But also in this question, I think it's a bit tricky in
Yeah.
terms of
Yeah.
how the mindsetters can also write the tone and the note, because there's like a difference of the first characters, the T and then N.
Yes, yes. Okay, a very good one, because you will look at tone and say, maybe I'm still talking note. That's why I put both of them there to say, look, we're talking mainly note in musical terms rather than tone. The tone is the way you speak to other people, that sound that you produce, showing whether you're angry or okay.
All right, let's do the last question.
All right.
Lenman says, will we ever be asked to calculate interferences in longitudinal and transverse waves?
That is definitely possible. You can be told that one crest is 3 centimeters, the other one is 2 centimeters, out of phase, okay, out of phase. For example, this is just an example, and then they say to you, they are moving towards each other, okay, that direction and that direction, and they say find the resulting amplitude of this wave. They are going to meet at some point, and when they meet, there will be destructive interference. These two will be removed here, so -2. So what will happen there? The resulting one will be that one, and in this case, no more 3, but just 1 centimeter. I think you can see that. Beautiful.
Awesome. Thank you so
Yeah.
much, Mr. TK. Thank you for your time and really appreciate learning with you
It's
today.
a pleasure. It's a pleasure indeed. I enjoyed the lesson. I hope you enjoyed it at home there.
Awesome. Thanks to you, Mindsetters, for tuning in. We'll see you some other time for a great lesson. Peace.